and he is going to speak on Plethysm and the restriction problem in algebraic combinatorials. Over to you, Shomadit.
Okay, is my voice fine? Yeah.
Yes, it's fine.
Yeah, so I'll start. So first of all, thank you to the organizers for the opportunity. So I'll talk about this Plethysm and the restriction problem in algebraic combinatorics. So today morning, Professor Amritanshu also talked about this restriction problem. So I will connect this to Plethysm and throw some interesting problem on this. So first of all, I'll start with symmetric polynomials and functions. So what are symmetric polynomials? So you take invariable polynomials and look at only those polynomials which are invariant under any permutations. So usually, I mean, in this talk, I will only restrict myself over integers. So this z x1, x2, xn and the Sn invariants of that are the symmetric polynomials in n variables. So for example, you have h2 in two variables. So what are these? These are all monomials in x1 and x2 of degree 2. So you have x1 square, x1, x2 and x2 square, and you sum them up. So this is also known as complete symmetric function. So this elementary symmetric function E2, for example, in three variable. So these are, so there are three variables. So you are allowed to take two of them at a time and you are not allowed to repeat. So you get x1, x2, x1, x3, x2, x3. And for example, this P3, these are called power sum symmetric functions. So you raise every variable to some power and you add them up. So now if you restrict yourself to only finitely many variables, so these are usually known as polynomials. But if you allow yourself to take infinitely many variables, so these are known as symmetric functions. So for example, when I talk about this H4 at infinitely many variables, let's say x1, x2, x3, this countable infinitely many variables, this means you sum all the monomials of the form x power alpha, where mod alpha is 4. So by x power alpha, I mean this thing. This x1 power alpha 1, x2 power alpha 2, this alpha 1, alpha 2, alpha 3, all are non-negative integers and they add up to 4. And this is the notation x to the power alpha to denote that thing. So these are the general definition of Hn, En and Pn, as I said. So now there are some interesting class of symmetric polynomials. So these are known as Schur polynomials. So how these polynomials are defined? So first you take a partition lambda 1, lambda 2, lambda n, and then you draw the Young diagram of that. So how do you draw a Young diagram? So for example, here I have drawn the Young diagram for the partition 2, 1, 0. So when you have lambda 1, lambda 2 and up to lambda n, then you have lambda 1 many numbers in the first rows, lambda 2 many numbers in the second rows, and you arrange them in a left justified manner. So that's the Young diagram of 2, 1, 0. Now so now there is something called the semi-standard Young tableau. So what are these? So I will feel this Young diagram by numbers from 1 to 3. So in general, if you have lambda 1 to lambda n, you want to fill them by numbers from 1 to n. So here I have lambda 1 is 2, lambda 2 is 1, and lambda 3 is 0. So this is a Young diagram. So you fill the diagram by 1, 2, and 3, but you have to follow a rule. So what is the rule? So the numbers in each row has to be weakly increasing and numbers in each column have to be strictly increasing. So weakly increasing condition in rows and strictly increasing condition in columns. So you get all these fillings 1, 1, 2, 1, 2, 2, 1, 1, 3 and so on. So associated to this semi-standard Young tableaus, there is a statistics which is just the weight of the tableau, alpha 1, alpha 2, alpha 3. So what are alpha I? The number of occurrences of I in a particular semi-standard Young tableau. For example, the first semi-standard Young tableau is 1, 1, 2. So 1 occurs 2 times, 2 occurs 1 times, and 3 does not occur. So the weight of the tableau is 2, 1, 0. If you take the tableau 1, 2, 3, for example, the last semi-standard Young tableau, so 1 occurs once, 2 occurs once, 3 occurs once. So the weight of the tableau is 1, 1, 1. And then you raise these weights to the power of your variable x1, x2, x3, and you sum them up. And that is your Schur polynomial corresponding to the partition 210. So we can do this for any partition of length n in n variable. And interestingly, yeah, so this is general definition of Schur function, sum over all semi-standard Young tableau x to the power weight of t. So now here is an interesting theorem that if you vary your lambda over all partitions of n, then that forms a basis of all symmetric polynomials in n variables. So first of all, this is not a trivial fact to verify that this s lambda x1 to xn are in fact symmetric polynomial. So first you have to check that, and then you can show they in fact form a basis. And again, if you are not if you don't want to restrict yourself to finitely many variables, you can take infinitely many variables, and this becomes a formal power series. And in the context of formal power series, we usually call them Schur functions instead of Schur polynomials. So for example, if you have infinitely many variables, then you can fill this diagram by any number, any integer, 1, 2, 3, 4, 5, whatever you want, but you have to follow the condition that on each row it is weakly increasing and on each column it is strictly increasing. And you will get your Schur function. So now I want to introduce one interesting operation on the ring of symmetric polynomials, and then I'll go to symmetric functions. Okay, so you take two, so what are Plethysm? So you start with two symmetric polynomial. So I will demonstrate by one example. So let's say I want to define H2 Plethysm H2 on two variables. So what are these? So first of all, inside the bracket you have h2, so you have to expand h2 in two variables. Then what you get, x1 square, x2, x1, x2 and x2 square. Then you plug in these monomials instead of the variables in h2. So basically you substitute the variables in h2, let's say in three variables x1, x2, x3, by this monomials x1 square, x1, x2 and x2 square. So then if you write down the expansion, it will give you this thing: x1 4, x1 3, x2, 2x1 square, x2 square, x1 x2 cube plus x2 to the power 4. And instead of symmetric polynomials, if you have symmetric functions, you can do the same thing. So what is h3 h2? The symmetric function h3 h2 is just the formal power series. And how it is defined? So you take all the monomials of degree 2, x1 square, x1, x2, x2 square, x1, x3, and so on. So we have this countable infinite collection of monomials, and you plug in place of the variables for h3. And similarly, you can also define this hn Plethysm capital H, where capital H denotes this h0 plus h1 plus h2 plus dot 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 up to infinity. So what will be hn Plethysm H evaluated at these variables x1, x2, x3? This is hn of y1, y2, y3, where yi's are itself all possible monomials in the variables xi. So usually inside the bracket, if you have some hk, then your collection is all monomials of degree k. But inside, when I write capital H, then I do not have any restriction on the degree. So the degree of the monomials in the expansion of H and H, this is not in fact bounded. So that is one difference between symmetric polynomial and symmetric function. Okay, so this is the Plethysm. Now why this is relevant to our restriction problem? Okay, so we are interested in the polynomial representation of GLNC. So what are polynomial representations of GLNC? This is a group homomorphism from GLNC to some GLMC, where your matrix coefficients are some polynomial functions in the entries of G. And it is a very well-known fact that irreducible polynomial representations of GLN of degree D is combinatorially parameterized by partitions of D into at most n parts. So this capital lambda of Dn denotes the set of partitions of D into at most n parts. And actually character of these modules, so these are known as while modules, this W lambda Cn, these are irreducible polynomial modules for GLN. And the character of these are exactly given by the Schur polynomials evaluated at n variables t1 to tn. So now here is the restriction problem. So you can think of Sn as a subgroup of GLNC sitting inside as the group of permutation matrices. And we know that irreducible representation of the symmetric group, those are parameterized by partitions of n. So now the polynomial representations of GLN are parameterized by partitions of some number d to at most n parts. On the other hand, representations of Sn are parameterized by partitions of n. And then you can ask this question that if you take a while module for GLN and you restrict it to the symmetric group Sn, then it will break up into irreducible representation of Sn, right? And then you can ask that how many times a particular representation V mu will occur inside this. So that is the question, that can you find a positive combinatorial interpretation for this restriction coefficients. So this is the Littlewood's formula, that the restriction coefficient R lambda mu is actually given by this this is the inner product, but you don't have to know what is the inner product. This is just same as the multiplicities of S lambda in the expansion of S mu H. So remember that I defined S mu plethysm H. So here I defined H and plethysm H in exactly same manner. You can define S mu plethysm H. And as I said, that any symmetric function can be written as sum of Schur functions because they form a basis. So this S lambda, so this multiplicity of S lambda in the expansion of this symmetric function S mu plethysm H, that is exactly the this restriction coefficient. So on an algebraic level, this is fine, but we want to give a positive combinatorial interpretation for this, and this is not known. So these are some questions, that can you count this combinatorially, or can you classify all lambda for which this W lambda Cn admits an Sn invariant vector. So this S lambda occurs in the expansion of H and plethysm H if and only if your while module W lambda Cn admits an Sn invariant vector. So even that is a hard problem. So in 2024, Sridhar and his collaborators gave a positive interpretation for this R lambda in, where lambda is a hook partition. So recently, actually, we have resolved this positivity problem for n less than or equal to 4. And we have some partial answers for general n. Okay. So this is one result, that so the first proposition is saying that you look at your partition lambda, and then you look at the first two parts, lambda 1 and lambda 2. And if the difference of lambda 1 and lambda 2 is large enough, then this restriction coefficient is always positive. So that means your while module W lambda Cn will always admit an Sn invariant vector if the difference of lambda 1 lambda 2 is large enough. This is one sufficient condition. Another sufficient condition we can give is that if no two consecutive parts of lambda are odd, then also you have this positivity of this restriction coefficient. So this R lambda n, so remember this R lambda n, so n means instead of mu, I'm putting n. That means it is just a one row partition n. And R lambda n means the restriction W lambda Cn to Sn, and then you are computing how many times V of n. So n means a single row partition n. So that means the trivial representation of Sn. So R lambda n positive means when your W lambda Sn invariance and Sn invariant vector. So yeah, and here is one theorem. So this is solved for, this is completely classified for n equal to 3. So the while module W lambda C3 that will admit an Sn invariant vector if and only if your B is odd and lambda is in one of the following form, BBB minus 2, BBB minus 1, and so on. And this collection might look a bit messy, but if you observe this carefully, so there's a pattern which is that this B is odd, and there is a long streak of odd numbers. If you observe all these partitions carefully, so there's a long string of odd numbers which are occurring successively. For example, here BBB minus 2, the BB is occurring uh, just next to each other, and then BBB in all these cases you can see. And roughly that's how you can try to guess a pattern that in general what kind of lambda uh, will give you this inner product 0 actually. So this is for n equal to 3, and for n equal to 4, only a week ago I also solved this, that your W lambda C4 will admit and Sn I mean S4 invariant vector if and only if uh, B is odd and lambda is in one of the following form. And in this collection you can also see that possibly there is a pattern that your B is odd and there is some long streak of same odd numbers which are occurring next to each other. For example, if you look at the last case, we have the B B B B B plus 2 B B B. So many odd numbers are occurring next to each other. And we expect that that is a general pattern for any a general in, this pattern will continue. Yeah, and so these are some open problems. So can you find a combinatorial interpretation for the multiplicity of S lambda in the expansion of S mu Plethysm HM? That is one open question. So recently Park Panova Swanson, they gave an interpretation for lambda with length of lambda less than or equal to 2. So just want to emphasize that even for partitions with at most 2 rows, this is a difficult problem, that how many times your S lambda will occur inside S mu Plethysm HM. Yeah, so I think that's pretty much what I wanted to say. So I'll stop here.
Yeah, thank you, Shomadeep. Any quick questions? Maybe we have time for one quick question.
So, how do you prove these results?
Okay, so the main idea is that so there is this coproduct in the ring of symmetric functions. So by using that coproduct, uh, I expand this H in Plethysm H. And from there, a great deal of information can be sort of churned out. So this Hn Plethysm capital H will break up into product of Hn Plethysm Hm, which is your usual Plethysms. And then inside each of the Plethysm, you can analyze that what kind of Schurs are occurring. So the main idea is using the coproduct in the ring of symmetric functions. So I would say that. So
Any more questions? If not, let's thank the speaker. Thank you, Shomadeep. Our next speaker is Viral.